Hi everyone. From this lecture, we will consider the multigate transistors. Today, we calculate the IV characteristics of the double gate MOSFETs. In order to improve the gate controllability, it is desirable to have multiple gates. The double gate MOSFET is one of multigate transistors. It has two gates. As a starting point of our discussion, we generate MOSFETs with a 20 nanometer thick channel. The oxide thickness is 2 nanometer and the channel is lowly doped. Constant source drain doping is assumed. Top and bottom gates are tied. The channel length varied from 20 nanometer to 200 nanometer. These figures are showing two extreme cases. Of course, we expect the short channel effect. How much is it? This figure shows the input characteristics at a drain voltage of 0.1 volt for a long channel device. The ID versus VG curve looks okay. However, when the channel length is reduced, the switching is not performed well. In the next slide, we will consider the threshold voltage, subthreshold slope, and DIBL. This is the threshold voltage. We define the threshold voltage as a gate voltage for drain current of 1 microamp per micrometer. For long channel device, it is about 0.35 volt. However, below 50 nanometer, the threshold voltage rapidly decreases. When the channel length is 20 nanometer, it is even negative in this example. The subthreshold slope is also affected by the channel length. For long channel device, the subthreshold slope is 60 mV per decade because the channel is lowly doped. On the other hand, when the channel length is reduced, the subthreshold slope is degraded. Of course, the DIBL is also affected. The DIBL is calculated from simulation result at two drain voltages 0.1 volt and 1.0 volt. Down to 100 nanometer, the DIBL is negligible. However, it is rapidly increasing as the channel length is decreasing. From these results, we can conclude that the channel length, such as 20 nanometer or 30 nanometer, is not acceptable. With a thinner channel, the previous problem can be removed. In this slide, we are looking at the IV curves obtained from 10 nanometer thick channel devices. They are red curves. The brown ones are for previous 20 nanometer thick channel devices. For a channel length of 200 nanometer, two curves, red and brown, looks similar. However, when the channel length is reduced down to 30 nanometer, the 20 nanometer thick device suffers severely from the short channel effect. On the other hand, the thinner channel device shows much better characteristics. In order to see the impact of the double gate structure, we intentionally remove the bottom gate. So now our structure has only the top gate. The simulation results are shown as blue curves. As you can see clearly, without bottom gate, the short channel effect cannot be suppressed. Simply speaking, with the multi-gate structure, we can further scale down the channel length without a severe short channel effect. Okay, that's it for this lecture 19. In the next lecture, the quantum confinement effect will be discussed. Thank you and see you later.